Oh, a sketch. Yeah. Oh, so the members are requested to take the seats. We'll start shortly. A very good morning to all. Our distinguished guest, Dr. Dibyendu Roy, respected faculty members, and dear students. David Hilbert presented his famous list of 23 important and hard unsolved problems at the International Congress of Mathematicians, many of which are solved today, except for a few, notably the Riemann hypothesis. In the conference, after posing the problem, he said in German, "Wir müssen wissen, wir werden wissen," which translates to "We must know and we shall know," by David Hilbert. He embodied ultimate scientific optimism. It is a reminder that curiosity and the drive to know are essential for any scientific journey. Guided by the spirit of exploration and discovery, it is my privilege to introduce the Raman Lecture Series, an academic initiative of the Physics Association. On behalf of the association, I extend a warm welcome to all of you to the second lecture of this distinguished lecture series. About the series, the Raman Lecture Series is envisioned as a platform that brings together student, faculty, and distinguished researchers to extend ideas, explore emerging frontiers in physics, and cultivate a deeper appreciation for scientific inquiry. We hope that this series will inspire curiosity, promote collaborative learning, and encourage the pursuit of excellence in research and innovation. The series is named in honor of Sir C.V. Raman, the first Nobel laureate in science, whose pioneering discovery of the Raman effect transformed our understanding of light and matter. His unwavering curiosity, commitment to scientific excellence, and passion for discovery continue to inspire generations of physicists. Through the Raman Lecture Series, we hope to carry forward that spirit of inquiry and innovation. We are truly honored to continue this journey with our distinguished speaker, Dr. Dibyendu Roy, professor in the Theoretical Physics Group at the Raman Research Institute, Bangalore. Dr. Roy's research focuses on condensed matter physics, non-equilibrium, statistical mechanics, and quantum optics, with particular emphasis on waveguide quantum electrodynamics, non-Hermitian topological systems, open quantum systems, and quantum chaos. On behalf of the Department of Physics, I extend a warm and heartfelt welcome to you, Dr. Roy. Thank you for having the time to be with us today and for sharing your knowledge and insights. Without any further delay, I invite Dr. Dibyendu Roy to deliver the second lecture of the Raman Lecture Series. Questions will be taken towards the end of the talk. Thank you, and over to you, sir. Yeah, it could also be interactive. So if you have questions in between, sir is entertaining those questions.
Okay, so can you hear me without this, hopefully, or I need to use this? I have to use this. Oh. Okay, so. Okay, can you hear me now? Okay, very good. Okay, so let me begin by thanking the organizer, particularly the students and also Professor Lebna for the invitation to come here and present our research here. I am going to talk about chaos in quantum systems. And I have been told that there will be mostly students here who have done like third and fourth year of bachelor and first year of masters. So I hope that I will be able to give you some essence of my research in chaos in quantum systems. And as I said to Kamesh, that please ask me question in between if you can't follow me, because it's better you talk to me so that I can explain what I am trying to talk. Okay, so please stop me. I will be happy to answer, then just go through my slides. So I believe that most of you have already taken one course at least in statistical mechanics, right? And also probably one course in quantum mechanics. And today's talk will be kind of a mixture of both of these topics. So I will try to talk about particularly statistical mechanics, and I will show that how to understand foundation of statistical mechanics through the lens of kind of chaos. So statistical mechanics is one of the most successful areas of physics. It was kind of introduced already 170 years before. And statistical mechanics, why we learn? Because we want to understand thermodynamic laws, which many of you again have learned before, even statistical mechanics, through microscopic description. And in the process of microscopic description, we introduce something called microstates. So these microstates in classical systems we describe through kind of phase space points. So you know that classically we describe any system on phase space made of position and momentum, and we want to describe these classical states through these microstates. And once we know this microstate, classical statistical mechanics says us or gives us few postulates. One of the first postulate calls equal a priori probability. I hope you have heard this, right? How many of them you have not heard about this? All of you have heard it, this one, equal a priori probability? Okay, very good if you have heard. So equal a priori probability says about these microstates that for an isolated system, it can be this room where we all are out and the room is closed, all the windows are closed, and we have gas particles inside this room. So this is an isolated system. So for an isolated system in thermal equilibrium, so this room is in equilibrium at room temperature, which may be today 30 degrees Celsius. So for an isolated system in thermal equilibrium, all accessible microstates consistent with some fixed external parameter, which for this room may be total energy, number of particles, and the volume of the room. So this defines these isolated systems, and all the accessible microstates are equally likely to occur. This is what says by equal a priori probability. Like the system, the room which is in my system, or isolated room which is my system, is equally likely to be any of these microstates. So this is equal a priori probability. So this postulate is very essential because this is through which you may have heard that we define microcanonical ensemble. So microcanonical ensemble defines through this postulate. Now once this postulate is defined for these microstates which forming an ensemble, we want to do some measurement of observable, which can be the total energy of the room or momentum of these particles in the room. So momentum of the particles of this room, and when we do these measurements, the system will not be in one particular microstate. It will travel through different microstates. So any measurement process will allow the systems to move around these microstates. And this will give you a measurement. But now we want to understand that how to give that measurement of the observable, how to calculate from microscopic description through these microstates. And this postulate, which is called ergodic hypothesis, tells us how to do that. So over a long period of time, an ergodic system in phase space visits all accessible microstates of the same energy. So that means all the possible microstates. So I give a simple picture here. So for example, if you have simple pendulum, which I define by their position and momentum, we know that we can draw a phase space of constant energy like such. such region is describing phase space with energy E and maybe E plus delta E. So this is the region which is, I have all these microstates, and what is said here that the system can access all these microstate over time, and because of that any time average equals to ensemble average. I'm sure you have heard also about this ergodic hypothesis or ergodic system. Now question is, when a system is ergodic and when it is not. Are all systems ergodic? Okay, so what do you believe? Will you believe, or what do you believe? Let's have a vote. How many of you thinks the system will be always in ergodic, or in some sense you will have that any, like this room particles will go through all the accessible microstates. So you think like it will be ergodic, right? Please vote, no problem, because it's a democratic country and you all can vote. Okay, so how many of you thinks it will be ergodic? So I don't know, only 2% has said it can be ergodic, or maybe 4-5%. And I hope the other person don't know or thinks it's non-ergodic. So the thing is, and this is the talk about, that many systems are not ergodic, and if they are not ergodic, we are not supposed to apply statistical mechanics. So if we can't apply statistical mechanics, we really cannot calculate even what we know every day. Anyone, like either in astrophysics or electronics or in electrodynamics, everyone needs to start with statistical mechanics, because that's what I said, it's one of the most successful areas of physics. So you need to apply statistical mechanics, but I am saying like most system may not be ergodic. So I cannot even apply equilibrium statistical mechanics to calculate any physical quantities, which as a theoretical physicist one would like to know. So this talk I will discuss that when a system can become ergodic. And for that I will start with maybe a simple example here. This is a top, you can see this, I have a top and I am thinking there is no friction in the ground. So this top is spinning or precessing, and then what is happening, someone is kicking it periodically over time, discrete time. So the top is spinning or precessing, and someone like at time t equal to 1 second kicked it, and then t equal to, it's allowed to precess, and again t equal to 2, it's again kicked. So periodically someone is kicking this top, but in between two kickings the top is precessing freely. So such problem one can study classically, right? Because you have studied rigid body problem and all these things. So you can study such problem and study the dynamics of this problem in maybe phase space or state space. So for such this spinning top or precessing top, the state space is made of the angular momentum. So for example, for this top, I can have 3 angular momentum, Jx, Jy, Jg, and if I do not have friction, the total angular momentum will be conserved. So the state space can be presented by the sphere surface. So why? Because I have 3 angular momentum, let's call Jx, Jy, and Jg. But I said like total angular momentum, J square is conserved, which is, I can write like Jx square, J square by Jg square. Since it's conserved, this kind of gives a sphere in terms of like Jx, Jy, and Jg. And the spheres which I am drawing is that one. And since J square equal to Jx square plus J square, Jg square, my state space lies on the surface of this sphere. So what I am trying to show here, that when you kick this top with small kicking, then you will see the state space like that Jx, Jy, Jg plane, the top is only accessing few microstates. So all the microstates or all the points on this sphere are microstates for this kick top, but for small kicking, only one line is accessed by the top. So that is against this idea of ergodic hypothesis, which says the system will visit all accessible microstate. So the kick top for small kicking is not accessing all the microstate on the surface of the sphere, and that is not an ergodic system. So which I was saying, like many systems are not ergodic. And I cannot apply easily the postulates of statistical mechanics on such system. But now if I increase the kicking strength, so I'm kicking it really high or a large kicking. So in that case, what we will see over time, all the microstate are actually accessed by this kick top. So this one is ergodic. So this was not ergodic, this is ergodic. So by kicking strength increasing for such time dependent problem, because it's a time dependent problem because I'm pushing or giving energy at each kick to this isolated system, which I started for an isolated system, but in this case I have an isolated system like top, which I am giving energy by kicking at each discrete time. So for such system, I am seeing like at large kicking, I can access all the microstate, but for small kicking, I cannot access the microstate. So in this case, system is non-ergodic, and in this case, system is ergodic. And I will try to explain in this talk what really happens between this and this, that one system is ergodic and another is not ergodic. So this is the talk main motivation. Okay, hopefully this much is understood. So please, anyone who is not following, ask me, because at least this message should be there, and you spend 1 hour here, and if you really do not understand this much, so then I will feel bad, like I could not really explain what I am trying to explain here. So this is the main message, that we want to understand the second postulate of statistical mechanics. In fact, now first postulate is still debatable, and many people are claiming that maybe we have to discard first postulate because it's very hard to prove. People are having hard time to prove the first postulate of statistical mechanics, but for second postulate, at least there are some studies, or there are many studies, I will say, which are trying to show like when system will become ergodic and we can apply ergodic hypothesis. And one way to study this is through the study of chaos, which is the topic of this presentation. So I will talk first, or I will discuss little bit first, chaos in classical systems. Then I will come to my main topic, which is chaos in systems or quantum systems. So first I will talk chaos in quantum system with semi-classical limit. That itself may not be familiar with many of you, and I will try to explain what is this semi-classical limit means. So first I will talk for such system which has semi-classical limit, such quantum system which has semi-classical limit. And for such system, there was a conjecture in 1984 by these three gentlemen, actually not all gentlemen, so one is lady. So by Boyas, Gianni and Smith, they put this conjecture which says like how to identify chaos in quantum system with semi-classical limit. So I'll little bit explain that, or maybe I will explain it in details, that second part. And then third part I will come something a very fundamental idea in again mathematical physics or theoretical physics called random matrix theory. I'll come to that point little bit. I'll just say what is random matrix theory and what is spectral form factor. I'll come to those points, and finally I will talk, which I have been doing research for last maybe 8-9 years, this many body quantum systems without semi-classical limit. How to understand chaos in systems which do not have semi-classical limit and which are not just single particle but made of many particles, which our universe is. Universe is not made of single particles, so they are made of many particles. So this is the kind of direction where I am doing research with my PhD students. Vijay Kumar, he is an excellent researcher. He is going to finish soon his PhD. So with Vijay and with of course Professor Thomas Prozen from University of Ljubljana, Slovenia. And Professor Prozen is a leading expert in statistical mechanics, particularly on quantum chaos and quantum transport. So let's start with chaos in classical system. And I hope again you have seen what I'm going to talk here, mostly you have seen in your bachelor courses. This is what I'm going to talk, mostly classical mechanics. So please, again, as I'm saying, ask me question if you are not following. So I'm going to talk about simple classical mechanics. And as I'm saying, like hopefully everyone has studied this classical mechanics. And we generally describe classical mechanics in like different description, either Newtonian mechanics or Lagrange mechanics or Hamiltonian mechanics. So they all are equivalent description. So they give us like some kind of dynamical equation, and we try to solve such equation, and from that we try to predict the evolution of system. So when you do such things, what you finally find, there are two type of motions in general in classical mechanics. Classical mechanics which are described by Hamiltonian. I'm sure all of you are familiar with Hamiltonian, right? Who is not familiar, can you please raise your hand? Don't worry, even it's not required to understand everything, okay? So if you are not familiar, I will also try to describe maybe through Newtonian mechanics, but I am going to describe mostly through Hamiltonian because that's what quantum mechanics is very close to. So Hamiltonian mechanics, when we do what we do, we generally write a Hamiltonian of a system and then write Hamilton equation of motions. So from there we can get some equations, and with some initial conditions we like to solve such equation to predict the future. That's what we do for, again, astrophysics or particles in soft condensed matter experiment or biological systems. Everywhere we can apply classical mechanics and understand the dynamics of particle. And in such systems there are two kinds of motion, as I said. One called regular motion for integrable system. What I mean by integrable systems, the systems whose Hamiltonian equation you can solve analytically. And I give an example. You must have solved simple pendulum problem, right? So that is an exactly solvable model or integrable system, because there you can easily calculate how displacement changes with time from some initial displacement. So that is an example of integrable system, and for such system I am calling the dynamics is regular. What I mean by regular, I will show you in my example here, but also you can say like this is an example of regular motion where you have a periodic orbits over the state space. And when you cannot solve such Hamiltonian equation analytically, then such systems generally can be called not exactly solvable or non-integrable system. And dynamics generally for such systems become chaotic. So how we generally describe chaos in classical system, or the classical chaos is identified through something called hypersensitivity of phase space trajectory to initial perturbation in initial condition, and long trajectories uniformly filling the available phase space. So let me explain these two part of the sentence. One, it's called hypersensitivity of phase space trajectory. So when I was saying phase space trajectory, so it's like evolution in xp space of starting from some initial points. So it can be like, for simple pendulum again, I start from Q0, P0 point in phase space and evolve over time in a trajectory like this, maybe. So this is time evolution, where this Q0, P0 points you start and then you evolve over time, which will be like maybe going through some QT and PT points. And this trajectory, if is highly sensitive, that I make a small change in this initial condition, instead of Q0, P0, I start now Q0 plus delta and P0. So this is very small change, delta, and I start here. And if this trajectory now do not follow exactly these things but becomes very different on phase space, then that is like hypersensitivity to the initial condition perturbation, which like these two trajectory I tried to draw. So that is one way to detect that when system will be chaotic. If it shows like hypersensitivity to initial condition perturbation, I'll call that system is chaotic. And if it is showing like the two trajectories following each other, even though there is little change in initial condition, then that I'll call regular. And the other thing is the trajectory uniformly filling the available space over time is like this case where I said like I start with one point, but over time all the phase space accessible points are visited by the system. So these two conditions, if they are satisfied, we can call the system is chaotic. And I will give a simplest example of such chaotic system is made of two bar of length L and mass m. So the length L for each of this bar and mass m, which is equally distributed. So such things can be is called double compound pendulum. So I am sure you have read about pendulum. I do not know how many of you have seen these systems. This is little extension of the pendulum. So generally one bar you can call it pendulum. So this is double compound pendulum. And what is these systems are like, you can start with some small angle here for theta 1, even theta 2 can be 0, and you can see like under gravity these two bars will start move like this kind of things which is shown below. So for such problems, one will see like if you have small angle swings, like these thetas are small, then the trajectory will be mostly showing regular. And again, regular means there is no such initial condition perturbation exponential sensitivity, or the long trajectories uniformly filling the phase space. So for small angle swings, I will see the trajectories are mostly showing regular behavior, and for large angle swings, it will show chaotic. And I will show you the trajectories which I was trying to show. But before that, I need to say how we describe these motions. So generally what we do, again in classical mechanics, that we take some points in the center of mass of each bar, so x1, y1, x2, y2, and in terms of that I write first the linear kinetic energy, rotational kinetic energy, and this potential energy to define the Lagrangian. And then from Lagrangian we can convert also these things to Hamiltonian, which is written here. So Hamiltonian is just used in terms of angle and the corresponding generalized momentum. And this Hamiltonian, once we know the Hamiltonian, we can write the Hamiltonian equation for these angles and for momentums. I hope this is familiar to all of you, that you know how to have this how to have this Hamiltonian, and from there Hamilton equations. Now this kind of thing, simple experiment one can do even in bachelor labs, and people have done and written popular paper like in American Journal of Physics, that how to do such experiment with double pendulum and see trajectories showing classically regular or classically chaotic behavior. And to do that, what I will do, I will write these Hamilton equations and try to solve them for choosing some initial conditions. So what I am choosing here, I am choosing that I am choosing here initially theta 2 0 is 0, so that means this bar is here, and theta and p theta 2 is also 0, the momentum corresponding to theta 2 is 0, p theta 1 is also 0, but only theta 1 at t equal to 0 is non-zero. That is what I have taken. So I have taken all other initial values to be 0, and theta 1 is non-zero. And I am trying to plot the phase space trajectory on theta 2 p theta 2 plane. So for the lower bar, their angle and corresponding angular momentum. And what is the initial condition I am setting? For here I have taken two different initial conditions. One case theta 1 I have taken pi by 10, small angle, and another case I have taken theta 1 to be pi by 10 plus 0.001, very small change in the initial condition in theta 1. Now if I do this two trajectory and look the time evolution from the initial point, so initial points for theta 2 p theta 2 was 0, so it starts from here and they followed such trajectory which you can see here. So now you see that two different initial conditions exactly follow each other here. So for small angle swings, two trajectories are following each other. And I hope this kind of says like what I was saying, it is regular because there is no exponential sensitivity to phase space perturbation. So this, for small angle swings, theta 1 is small, pi by 10. So I see the two trajectories for small initial condition perturbation are following each other, and that is a regular dynamics. Or in some sense, why it's regular? Because again, I do not know if you have learned this, that pendulum, when you take small angle swings, you can solve it analytically. So it is becoming exactly solvable systems, even for couple pendulum, and because it's exactly solvable, so I can find the two trajectories even for small different initial condition, but they are exactly following each other. But now if I take this theta 1 0 large swing, in this case pi by 2, so I change from pi by 10 to pi by 2, and the perturbation I kept small only 0.001. So I now look to trajectory, one by blue and one by red. Again theta 2 p theta 2 was 0 there, so start from here. But now as I see that two trajectory initially are following each other, but after some point like here, they start to show difference. So they are not following each other anymore, and the two trajectories, this red and blue, started becoming different, and after maybe sometimes here, maybe some 5 seconds, you see the red ends here and blue ends here. So they are very far separated in the phase space. So on the phase space, these 2 points are very far separated, which surely shows that small delta in perturbation in the theta now has grown to such big difference in theta. So this we can write as something called, in terms of this Lyapunov exponent, which say this theta 2, the theta 2 here for two different initial conditions, what I call 1 and 2, they are exponentially growing over time when lambda is positive. So exponential of lambda t. So this separation is exponentially growing over time, with the measure of this growth is by lambda, which is called Lyapunov exponent. So initially there was small separation delta naught, which is 0.001, but then over time this separation has growth exponentially, and that shows exponential sensitivity to initial condition perturbation. And this is a measure of classical chaotic dynamics. So if you have a system which shows that two trajectories are exponentially separating over phase space points, so then we will call it a signature of chaos, classical chaos in such dynamics. And double compound pendulum can give both the dynamics, like regular dynamics for small angle swings, where we can solve them as an exactly solvable model, but for large angle swing, I cannot solve such problems, and because of that, this leads to exponential sensitivity. And I have not shown here, if I really wait long enough, each of these trajectory will fill the available phase space. So that is the other signature calling that it is a chaotic dynamics. And this Lyapunov exponent, I have tried to plot here, this lambda, which shows the exponential growth, lambda with this theta 1 0 value, which I was taking as initial condition. So as you see, for small theta 1, like when I have pi by 10 somewhere here, that lambda is mostly 0. So lambda 0 means there is no growth, because e to the power 0 is 1, so there is no growth of no separation, no growth of these two different initial condition separation. So mostly here lambda is 0, but after certain point of this theta 1 0 value, which is like pi by 2 will be near here, so you have lambda non-zero large value and it's growing. So this Lyapunov exponent is also something what people calculates to calculate that how much chaotic behavior is there in such system. So this is where I will stop about classical chaos. And again, if you have any question, which you are none of you are asking, but now I have to progress. So anyway, this is where the mostly classical chaos is about. Now I will go to quantum description. But before that, I need to explain that the main problem that to define such phase space trajectory and to explain things based on this phase space trajectory for classical chaos will not work for quantum systems. And this, I don't know if you are familiar again. So in quantum mechanics, we learn about Heisenberg uncertainty, which says like we cannot simultaneously detect both position and momentum with precision. So this Heisenberg uncertainty says we really cannot have a phase space description for quantum systems in general. Okay. So since we do not have a phase space description when Heisenberg uncertainty is important for quantum system, so we cannot just look phase space description and this hypersensitivity in initial condition perturbation to detect chaos. So then how to do that? In fact, I have not written here or I have not explained here, but even one can show the classic quantum mechanically, if you have two initial states which are little different, the separation of the time evolved state will remain same in quantum evolution because quantum evolution is unitary. So because of such unitary dynamics and Heisenberg uncertainty, one cannot describe quantum system chaos following the classical kind of description. So because of that, even though classical chaos was starting in like 1890s, the quantum chaos only started in 1980s. So 1890 to 1980. So almost 90 years it took to understand chaos in quantum systems, even though quantum mechanics started by 1900 or 1920, whichever you take, old theory or new theory of quantum mechanics. So it took a lot of effort to understand when and how to even describe chaos in quantum systems. And why it is important? Because we don't want to do statistical mechanics only for classical system. We want to do statistical mechanics also for quantum system. And to do the statistical mechanics, we need to have something like this ergodic hypothesis. And for that, we need again to understand chaos in quantum system. So for that reason, we need to understand chaos in quantum systems. And I will now give a simple model where we'll be able to understand chaos in quantum systems. And that is that top which I have given. It's a kick top. So I have shown you a top already in my second slide. So this top, now I will think this top as a quantum mechanical problem. So the top, as I said, top is made of angular momentum. When you do not think of the friction, so it's a closed system or isolated system. So top can be represented by an angular momentum. So if the top is just, let's call, precessing around y-axis, the omega jy represent that top. So when the top which I was showing is around y-axis precessing, so my angular momentum around y-axis shows that top. So this part, first part of this Hamiltonian, which I am writing, is a quantum Hamiltonian for a freely precessing top. Now, second part, what is saying that I said like I was kicking that top in regular interval, and that regular interval is written by this t minus n tau. So tau is the time over which I am not doing anything, and after each tau, I am kicking the top, and n is numbers 0, 1 to all this. So each tau, 2 tau, 3 tau, I am kicking. So in between this kick, the top is just precessing freely. So if this is my time axis, so t 0 to tau, there is free precision by jy angular momentum, but at t equal to tau, there is a kicking along z direction by this term h bar k by 2j jg square. So the kicking is along the z direction, and that kicking, what is doing, if top was precessing like this, it just kicked in another direction and moves to that direction. Then you will try to precess like that, and again you kicked, it start to precess like that. So the kicking is doing, just changing the direction around which it was spinning. So this is the Hamiltonian, which we can think about that top, and this so as I said, like at tau, 2 tau, 3 tau, this kicking is there. And the kicking is by this Hamiltonian which has jg square and free precessions by jy, two angular momentum. And again, if you have learned quantum mechanics, you have seen that there is non-commutativity of the operators or angular momentum given by that relation, like ji jj is equal to I h bar epsilon I jk jk, where I, j, k all runs x, y, z, three coordinates. And j is the total angular momentum quantum number. So like j square has angular momentum given by j into j plus 1, which you guys who are taking atomic physics might have seen that kind of things. So this is this top, which is kicked at regular interval. Now what I am interested to understand, I want to understand the dynamics of this problem. And I will try to understand this dynamics both in the classical regime as well as quantum regime, and identifying classical regime chaotic versus regular behavior. I will try to understand chaotic versus regular behavior in the quantum domain. So that's the goal right now we are trying to do. For this I have introduced this model. Okay, so the model is introduced to understand first classical dynamics of such top, and then from classical dynamics I will try to infer what we learn about quantum dynamics or quantum chaos. Okay, so now I have to say like how to go to even classical limit of this problem. I don't know how many of you have already learned these things in quantum mechanics. So when you have learned quantum mechanics or theory or maybe hydrogen atom or a harmonic oscillator, you may be wondering that what is the corresponding classical description, because harmonic oscillator or pendulum not only exist in quantum domain, but they also exist in the classical regime, right? So how to understand the classical version of this called harmonic oscillator? So do you have any idea how to understand classical description from a quantum problem? Anyone? Okay. So what will happen? So when we study quantum mechanics, as I said, this non-commutativity of operators are very essential, but one can also say like quantum mechanics is also about discreteness of energy levels, because that's the quanta we are talking about. For example, hydrogen atom, a simple problem where you have like one electrons bound around this nucleus and they have like discrete energy levels. You must have heard that things in quantum mechanics study, and this is discrete energy levels are what is the quanta which we define the quantum mechanics. Now if you look this discrete energy levels given by principal quantum number n, now as you increase n, this principal quantum number, you know that at large principal quantum number, this energy separation becomes smaller. So they form like a continuum levels. So n, let's call 1, 2, 3, to if you go 100, you will see automatically the separation between, let's call n and n plus 1 levels becomes very small when n is 100. So they form continuum, and that continuum is a description of classical mechanics, because classical mechanics, we do not call their discrete energy levels, rather we call energies can be continuum. So at large quantum numbers, generally the problem are like classical. So what we will try to do to get semi-classical limit, we will think this problem of kicked off a large quantum number. And the quantum number, as I defined, the total angular momentum j. So if I take large j, this problem is like classical. And in that case, I can try to understand the corresponding dynamics, and from there I will try to kind of infer about the quantum dynamics. But to do these things, I need to understand how to define even time evolution in such problem, because I want to understand any observable how it's evolving. So the time evolution for a time dependent problem generally defined by this kind of U operator. What is, you must have again studied that it is nothing but like U is nothing but is evolution over a period. So I have a time dependent Hamiltonian like this. I am evolving it from maybe 0 to time tau, one period. So this evolution, if you want to do with a time order sense, so this is like you can call U operator. So it has a name, people call it fluke operator sometimes. So this U operator, the time evolution operator for a period 0 to tau, for this problem can be written down in a simple form like product of two evolution operator, because of this delta function kind of kicking Hamiltonian. So this U operator, what it will give, if you start with any initial state 0, how it evolves in time like n tau into a state n, which is like U to the power n 0. So this is giving the evolution of a state 0 to state n by evolution operator U, which is nothing but just like this Schrodinger equation which you have seen to define some time evolution operator like this. Now once you have this evolution operator, you can also say evolution of any operators, which I am here writing maybe this ji, which is component of this angular momentum. So I runs again x, y, z. So this can be jx, jy, jg. So jx, jy, jg after one time evolution can becomes jx prime, jy prime, jg prime, which are related by this relation u dagger ji u. So this gives the evolution of any operator, and that can be calculated for such Hamiltonian which is written here. If you do not understand, that's not problem. Okay. So with this we can define the evolution of the operator, and from that we can write that how it will evolve from any state 0 by this u operator and form this any state n. Now I was saying like this j square actually is something remains conserved. So quantum mechanically, to understand what remains conserved is like its commutation with Hamiltonian. In this case, j square one can show is commute with the Hamiltonian. So is j square commutes with this operator of evolution. Because such things that j square is commuting, our Hilbert space, which he mentioned in his talk, Hilbert's name or his introduction, so that Hilbert space of the quantum mechanical problem is made of these operators j square eigenvalues and eigenfunction. So we can define the Hilbert space through the eigenfunction of j square and jg, which is here I written by j and m. It will form for angular momentum j by 2j plus one dimensional Hilbert space. So why I am saying all these things? Because I want to understand the evolution of this problem in the Hilbert space or in the classical phase space in the semi-classical limit. So I first take the classical case. So classical case, what I will do, I am hoping that still what I am talking is within your scope of understanding. But I ask you to ask me question, because otherwise I am actually very confused what you are understanding or I am just speaking or not. Okay, so please stop me, because it's good to have discussion. Science is more about discussion rather than knowledge. Okay, because it's much more important to understand what I am talking. So what I am trying to say now, that I will try to understand for this kick top the dynamics both in the classical regime as well as in the quantum regime. So to understand classical regime, I will go to large quantum numbers, large small j value, and for that I redefine my angular momentums by this bold x, where we have written that bold x is the quantum operator j by its magnitude by small j. So now one can show that each component of this bold x, which I am writing by xi or xj, they will follow from the commutation relation something like I h bar by j epsilon I j k x k. So this is derived just by using, sorry, this pointer does not work. So in this relation, by putting this one, I get that relation. And what we see in xi xj commutation, if you take j, small j large, so you have like I h bar by small j where j large, so the right side becomes 0. So the operators which were non-commuting, here now they will commute at large j. So when something commutes, they are like classical variables. So instead of operators now, they become classical C number variables. C number is the complex number variables. So they lie again on a sphere, because x square you can show again commutes with Hamiltonian, because j square was commuting. And so xi, which will run like x1, xi, I will write as x1 as just x, x2 as y, and x3 as z. So this x, y, z, they now lie on the surface of the sphere, of unit sphere. So the state space now has become what I was trying to show originally, like this one. The state space of this x, y, z at this, what I was saying, jx, jy, jg, but now I have redefined jx, jy, jg as x, y, and z. And what happens? Then we can look the evolution of x, y, z. Again, from this relation, I will not get into those, because I am feeling like I do not know how much you are really following, and you are not asking me question. So I will not get into how we derive all these things. So what I will do, I will say like how to study this problem classically. So we'll just look these equations which I tried to describe in the quantum case. I will try to say like in this limit, I can redefine those equations in terms of this. So now these are like x prime, y prime, z prime is after 1 tau evolution. What is this variable in terms of a tau equal, means before this evolution in terms of those variable. So x, y, z without prime is, let's call t equal to 0, this variable. And after t equal to tau, these variables are x prime, y prime, z prime. This relation gives how the evolution happens from x, y, z to x prime, y prime, z prime. And this you can write as a map. It's called kind of a nonlinear map, because this equation, as you see, has a nonlinear function of x, y, z. So that x prime is a map of f of x, which is a nonlinear function kind of. So with this, I know that evolution of this x, y, z to x prime, y prime, z prime. So I can do this evolution, and I will not get into all this, what I have written here, because these are important to understand dynamics of the problem. But let's not get into those, and try to say how this phase space trajectory of x, y, z will look over time. So this is shown in this plot. So what I am showing here, the kicked off classical motion on unit sphere, but instead of the full sphere, what I have done here is I am trying to project this sphere on the northern hemisphere in y-axis. So in some sense, in some sense, if I call that is my y-axis, I project every trajectory on this on a plane, yz plane. And once I project, I can now draw how the phase space evolution, or in this case state space evolution, or in the xg plane. So I have project everything from northern northern hemisphere along y-axis on a plane in the xg plane, and I am showing the trajectories. So okay, no problem. So on this trajectories, and to understand these trajectories, we need to see like what is happening. If I start with any point, how this trajectories looks. So this trajectories, as you see, for this is I am shown this trajectory for small kicking. The kicking is controlled by this kicking strength K. For small kicking, what is showing like trajectories which are forming periodic orbits. So these periodic orbits are signature which of the regular dynamics. So these periodic orbits are around some points which called fixed point, which is like when the map f of x is same as x. So it was like mapping was x prime equal to fx, but when x prime is x, that gives a fixed point where particle does not evolve. So in this case, one can calculate for such map, the fixed point are xg equal to 0. So this is like xg equal to 0, there is a fixed point, and particles or this kick top has trajectory which is around this fixed point in a periodic orbits. So these periodic orbits for small kicking is regular dynamics, but as I increase kicking from 2 to 3, I see there are still region which are fixed point like, and that fixed point is this fixed point which is z equal to minus x. So this is like g equal to minus x, this is equal to g equal to minus x. So at that, there are still fixed point and then nothing happens, and if I have orbits, it will form orbits like that. But rest of the things are uniformly filled. So that's like a signature of chaotic behavior. And as I increase the kicking strength further to 6, everything has filled. So this is fully kind of chaotic or ergodic dynamics. So at this space or this kicking, I am good to use equilibrium statistical mechanics. But at these kickings, here I have a mixed phase space, here I have mostly regular dynamics. So I can identify from here that what is for this kick top classical regime, what is the chaotic and regular behavior. Now I will explain just what is the quantum case this behavior. So this came from a very nice idea, as I said, from Bohias, Gianni and Smith, but it was actually initially thought by Professor Michael Berry in 1978. He was in IISc, Indian Institute of Science. He's a professor in UK, but he's very famous for something called Berry-Pancharatnam phase, which is also Pancharatnam phase discovered in RRI in 1958, which was rediscovered by Berry in 1984, almost like 25 years after. So this Berry, he was 1 year in IISc, Indian Institute of Science. That time he got very fundamental idea that energy levels of a quantum problem had signature of this regular versus chaotic dynamics. So that's where that you have the statistics of energy levels become important. So instead of looking dynamics directly, he's saying even the statistics of energy level had signature of regular versus chaotic. And how to understand that? Like, let's calculate for that problem of kick top with different kicking strength. So here K is the kicking strength, which I was saying in the previous slide, this kicking strength I am changing. So let's take, I am changing K 2, 3 to 6. Now I calculate for such kicking strength for a quantum problem now. So K is changed here. So 0, maybe here 2, here 3, here 6. So I am changing this kicking strength and calculating the levels, eigen levels of this Hamiltonian. But since this is a time dependent Hamiltonian, I cannot calculate eigen energy or eigen state for a time dependent Hamiltonian. Rather, what we should calculate, we calculate this evolution operator's eigen values. Evolution operator eigenvalue is defined like this. Evolution operator which I have defined is evolution operator eigenvalues defined like, because of some symmetry, it is defined for plus and minus sector differently. So m plus minus as e to the power minus I phi m plus minus m plus. So this is an eigenvalue kind of problem where phi m you can say like the eigenphase. So what I am plotting here, these 5 values, phi m plus minus values with kicking strength. What we observe, we see that small kicking, these 5 values, they are crossing each other. You can see that they are crossing each other a lot here in the small region. So one eigenvalue crossing another eigenvalue. But as we go larger kicking, the eigenvalues start to repel each other. This is what is shown here. So in the small kicking, eigenphases are kind of, or eigenphases or eigenvalues kind of crossing, and for large kicking, they are repelling. So they connected this idea to regular and chaotic behavior, because we know for classical problems, small kicking is regular, large kicking is chaotic. Now for quantum problem, they say that if you have eigenvalues or eigenphases crossing each other, then that is a signature of regular behavior in quantum problem. And if they avoid each other or repel each other, so they are signature of chaotic problem. So the label repulsion is a signature of chaos in quantum problem, while label crossing or clustering is a signature of quantum regular behavior. And this, to write in a more mathematical form, comes from like the difference of these eigenphases called label spacing. This label spacing is the difference of consecutive labels. So I take two values and take difference, and again I two values, they are difference, and create a histogram of this label spacing, which is P of S with S. Now this histogram for this region will show some kind of exponential in S distribution. But if you go in this region, it will show that this distribution has 0 at S tends to 0. Here S tends to 0, PS is 1. Here in all these three, S tends to 0, PS is 0. So this PS tends to 0 as S tends to 0 is a signature of label repulsion. Two labels cannot come closer to each other. That means their difference cannot be 0. Because of that, you have label repulsion giving something called random matrix theory distribution, and label crossing gives something called Poisson or exponential distribution. So this is called BGS conjecture, which says if you have a quantum system whose label spacing shows exponential or Poisson distribution, then you call it regular behavior for quantum system. And if it has something called this Wigner-Dyson or random matrix theory distribution, then that called chaotic behavior. So I will take 5 minutes and I will finish. Okay. So now I will not get into that how this distribution comes, all these things. So this is called random matrix theory distribution. I will not talk about random matrix theory, which is a very famous theory discovered by Wigner in 1950s, for which he was awarded Nobel Prize. So he was developing this theory in 1950s to understand how nuclear energy levels behave, and he developed this random matrix theory. I will not explain all these things. I will not explain spectral form factor, but now I will come to what we have been doing. So I said that I said this problem for a single kick top or single particle problem, quantum problem, single particle, with semi-classical limit, that large quantum number I go to classical. But then there are many problems which are not single particle, like everyday life is not like everyone are not made of single particle, we are made of Avogadro number of particles. And also we are like each of the particles are highly interacting, like electrons interact, repel each other, or electrons interact with protons and all these things. So highly interacting many body systems they are. And many times they do not have even classical analog. Why? Like spin half particles, they don't have any classical analog. I cannot take large angular momentum to make it classical. So what we are doing beyond single particle systems, beyond semi-classical limit, for many body quantum interacting systems, how to understand chaos. And how to understand chaos in this has become a very highly explored field for last 10 years. And I have been working in that direction, and we have developed new theories where we have been able to show, or we have been able to predict how to understand chaos in such systems. And in this process, we have developed a field which we now call many-body quantum chaos. What is that? Like understanding chaos or quantum chaos in many-body interacting systems. And this is where I will say, like, that's my research, which I am doing in RRI. Okay, so I stop. Thank you. Please ask if you have questions.
We can quickly take up 1 or 2 questions, if there's any. So, any questions? Okay.
Okay.
So, may I now request our faculty coordinator, Dr. Levna Chako, to kindly come forward and present a token of appreciation to Dr. Roy. On behalf of the Department of Physics, I extend our sincere gratitude to Dr. Dibyendu Roy for delivering such an insightful lecture under the initiative Raman Lecture Series and for sharing his valuable knowledge with us. I also thank our respected faculty members and our dear students for your enthusiastic participation, which made this session a success. With that, we conclude the second talk of Raman Lecture Series. Thank you all for being here. Have a wonderful day ahead.